Hello dear students, welcome you all. How is everyone? Okay, are you able to hear me? Okay, so let us start today's class. So this is the last class for shear force and bending moment. So we are discussing the previous year's prelims questions of engineering services examinations. Okay, so in today's class, this is the last class for shear force and bending moment. Okay, so for shear force and bending moment diagram, this is the last class. And in this class, we will be discussing all the previous year's prelims questions that were asked from 2015 to 2023. Okay, so let us start. First question. Question number 1. A rigid bar shown in the figure is hinged at A. Okay, so this is the hinged at A, is supported by a rod at B. Okay, so this is supported, this rigid bar, this is hinged at A, and this is supported by a rod at point B. So at point B, this is supported by this rod. Okay, and it carries a load W at C. So at point C, this is carrying a load W. Okay, so the resistive force in the rod, that means we are asked what is the resistive force in this rod. Okay, so what will be the resistive force in this rod? Let us say the resistive force in this rod is RB. Okay, RB is the resistive force in rod which is at point B. Okay, now how can we calculate RB? It is very simple. If we do summation of moment about A equal to 0. Okay, so bending moment at A will be 0. So if I do summation of moment about A will be equal to 0, I will be getting the value of RB. Okay, so moment will be coming because of RB and because of W. Okay, so perpendicular distance of RB is L by 2, and this is giving anti-clockwise rotation. So minus RB, let us take anti-clockwise negative. So minus RB into perpendicular distance is L by 2. So minus RB into L by 2 plus W into L will be equal to 0. So RB will be equal to 2W. RB equal to 2W. So correct answer is option D. Option D is the correct answer. Clear? Okay, let's move on to next question. The bending moment at C for the beam shown in the figure is, so we have to calculate bending moment at point C. Okay, so bending moment at C in this case. Okay, so what is the bending moment definition? By definition, we can say bending moment is summation of all the moments either towards the right of the section, or towards the left of the section. Okay, so I don't know the value of reaction at B, I don't know the value of reaction at A. So RA is also unknown, RB is also unknown. So if I calculate from the right side, I will not be able to calculate, because first I have to calculate RB and RA. Without RB and RA, I cannot calculate from right side. So what I will do, I will calculate from left side. So left side is like this. Okay, it is bent like this. Now bending moment at C, because of 1 kilonewton and because of 2 kilonewton, that I have to calculate. Okay, now because of 1 kilonewton, what will be the moment? Moment will be force into perpendicular distance. Okay, so for 1 kilonewton, perpendicular distance is this much, 1.2 meter. Okay, so and it is giving me which type of moment? Sagging bending moment. Okay, it will be sagging bending moment. So bending moment at C will be equal to 1 into 1.2. 1 into 1.2. Okay, it will be positive. Next, because of this 2 kilonewton, I will be getting force is 2 kilonewton, perpendicular distance is 1.6. So it will be 2 into 1.6. Now sine, this is also giving me sagging bending moment. So I'll add them. Okay, so I'll be getting 1.2 plus 3.2. So 1.2 plus 3.2 will be 4.4 kilonewton meter. 4.4 kilonewton meter. So here they have written it negative. Okay, so basically magnitude will be same. Now sagging and hogging depends on the reference face. If I take this outside face as reference face, then I'll be getting negative, and if I take this inside face, inner face as reference face, then I'll be getting positive. Okay, so here reference face is not decided, it is not given in the question, so it can, but depending on the choice of reference face, will get either positive or negative. Okay, so they must have taken outer face as reference. because on outer face, on this face, they are getting tension. Okay, so that's why they are getting negative. So never mind, magnitude is matching. Correct answer will be option. Okay, next question. Bending moment at A for the beam shown below. So what will be the bending moment at A? Bending moment will be force into perpendicular distance. So this is the force 40 kilonewton. 40 kilonewton, and perpendicular distance is how much? 180 minus 75, that means 105 mm. This is the perpendicular distance. Okay, so bending moment at A will be equal to how much? Force is 40 kilonewton into perpendicular distance is 105 mm. Okay, so I'll be getting 42 000 kilonewton mm. 40 000 00 4200 kilonewton mm. Correct answer will be option C. Correct answer will be option C. Okay, clear? Let's move on to next question. In the analysis of beam subjected to loads, the point with nil bending moment can be a. Okay, so in the analysis of beam subjected to loads, so we are having beams. Okay, these beams are subjected to some loads. The point with zero bending moments. Okay, so any point which is at which bending moment is zero. So if bending moment is zero, that will be, can be a point of contraflexure. Yes. Point of maximum shear force. So where bending moment is zero, do we say that shear force is maximum? No, it is opposite. When shear force is zero, then bending moment is maximum. Okay, when bending moment is zero, we cannot say shear force is maximum. So this is wrong. Then point of inflection, yes, correct. Okay, so which of the above statements are correct? Now we don't have any option which is giving me 1 and 3 as answer. 1 and 3 as answer. So is this question wrong? Maybe this question is wrong, and maybe we are not getting the question correctly. So what to do? Let us read this question again. In the analysis of beams subjected to loads, the point with zero bending moment, nil bending moment, that means zero bending moment, can be a. So it can be point of zero bending moment is called as point of contraflexure. It is also called as point of inflection, but we don't call it as point of maximum shear force. So can it happen that the point at which our bending moment is zero, at that point shear force is maximum? Can it happen? Yes, it can happen. It can happen. It can be a. So it is not saying that it will be a. That means it is necessary condition that it should be that point. Okay, but it is saying that it can be. So is there any possibility? It is talking about whether it is a possibility. Can means it is talking about possibility. Possibility. Is it possible? Is it possible that zero bending moment point will be having point of maximum shear force? Yes, it can happen. It is a possibility. It can happen. Okay, so they are talking about possibility. That means this is also correct. Okay, it is a possibility. This always happens. This always happens. But this is a possibility. So that means correct answer will be 1, 2, and 3. So this question, option D is the correct answer. Okay, let's move on to next question. Bending moment at A. So this point, at this point, bending moment at A for beam shown below with BD being a rigid bar. What do we mean by BD is a rigid bar? BD is a rigid bar. That means in this case, we want to say that there will be zero elongation, no elongation. Okay, no elongation. Okay, no elongation in this bar. Okay, so I want to calculate bending moment at point A. Okay, moment at point A, that I want to calculate. Here the load is acting 3 kilonewton. 3 kilonewton load is acting. So let us draw free body diagrams. Okay, let us cut a section here. Okay, and let us transfer this load here. Okay, let us transfer this load here. So and let us say in this bar I am getting a force, let us say R. Okay, so R is the force in this bar. So at this point, this is point A, this is point B. Okay, here R force is acting. Okay, here we are having point C, here R. Okay, and this 3 kilonewton, let me transfer this 3 kilonewton here. Let us transfer this 3 kilonewton here. So here we are having 3 kilonewton. 3 kilonewton. And when I have transferred this 3 kilonewton here, now because of this 3 kilonewton, there was an additional moment. There was a moment that was 3 kilonewton meter in clockwise direction. But if I have transferred here, that moment is no longer existing. So I have to introduce that moment also. So this moment is 3 kilonewton. Okay. Now, so this part can be represented as this. This whole structure can be represented by free body diagrams of AB and CD. Okay, AB and CD. Okay, let's forget this part. Okay, now I first of all, in order to calculate bending moment at point A, I have to calculate this reaction, the internal force in bar BD. Internal force in bar BD that I have to calculate. Okay, so R reaction I have to calculate. So what is the R axial force in this? In order to calculate R, what I can do summation of moment at point C is equal to 0. Bending moment at point C is equal to 0. Okay, so bending moment at point C will be equal to, because of this R, I will be getting minus R into perpendicular distance is 3 meter. So minus R into 3. Okay, now because of this 3 kilonewton, how much bending moment I will be getting here? I will be getting plus. Because of this R, I will be getting positive. Okay, if I calculate in terms of moment, okay, let me calculate moment. Moment and bending moment both will be same thing here. Okay, bending moment will also be 0 and moment will also be 0. Okay, so this is giving me anti-clockwise rotation. This is giving me anti-clockwise rotation. So I have taken negative. This will give me clockwise rotation, 3 kilonewton. Let me take it positive. So plus 3 into 3, and this is also giving me clockwise rotation. So plus 3 kilonewton meter, and this value will be 0. This MC will be 0. So my R will be equal to 3 3s are 9 plus 3 12 divided by 3 4 kilonewton. So R is 4 kilonewton. Now when R is 4 kilonewton, then bending moment at A will be equal to force into perpendicular distance. So bending moment at A, MA, will be equal to R into 3, and we have to calculate magnitude only, so no need of sign. However, this will give me negative bending moment. So R is 4 into 3, so I will be getting 12 kilonewton meter. So this will be the answer. Bending moment at A will be 12 kilonewton meter. Correct answer will be option B. Is it clear? Correct answer is option B. Okay. Next question. The bending moment diagram for the beam shown below is. Okay, so for this bending moment diagram for beam, see, rope tied at B. So this is a rope. Okay, it is tied at B. By some means it is tied at B, turned at fixed point E and on pulley at D, and this rope is going here. Okay, but it is not clear that if this rope is tied at C also or not. It is not clear, it is not given that this rope is somehow attached to the beam at C, or it is independent of the beam. It is not touching the beam, it is just going downward. This is not given in the question. Rope is tied at B, this is given, and rope is tied to the beam at C, it is not given. So what we will assume? At point B, this rope is tied here. This is given. But at point C, it is tied to the beam. This is not given. So we will assume that this is not attached. Okay. So if I draw free body diagram now, considering this, if I draw free body diagram, what I will be getting? See, this 2 kilonewton is constant over the string of the rope. Okay. This 2 kilonewton will be constant. Here also it will be 2 kilonewton tension only. Here also it will be 2 kilonewton. So basically, if I remove at beam, on beam, I am getting a force of 2 kilonewton here. Okay. Now this is not touching the beam. This rope is not touching the beam. So this rope is not having any effect on the beam. So at point C, there is no contact of this rope with the beam. At point C, the contact between beam and rope is not existing. Okay, so rope is tied at point B only. So if I want to draw all the external forces on the beam, I'll be getting only one external forces at point B here, and this external force is 2 kilonewton. This external force is 2 kilonewton and perpendicular distance is 3 meter. Okay, now bending moment diagram should be like this. At this point, zero bending moment, and here it is linearly increasing like this. So bending moment diagram should be like this, right? And 2 into 3, 2 3 is 6. It will be 6 kilonewton meter. It should be like this. Okay, if it is not touching here. Now, if it is not touching here, so none of the options is correct. None of the options is correct if we assume that the rope is not touching the beam at C. Okay, now that means rope must be touching the beam at C. Rope is tied at C also, and rope is tied at B also. Now if in this situation, if rope is tied at C and at B, and it is connected to the beam at these 2 points, if I apply a force of 2 kilonewton, this part of the beam will be resisting this 2 kilonewton or not? This part at this location, this 2 kilonewton will be resisted, yes. Okay, so the beam will be resisting some part of 2 kilonewton, and there will be somewhat less tension in the beam here. Somewhat less tension in the beam. How much less tension? Now that will depend on EI of the beam. That will depend on EI of the beam. If EI of the beam, EI means flexural rigidity. How much deflection will be here? That we have to calculate. Okay, then we have to derive some compatibility conditions. Then only we will be able to find out how much tension is coming in the rope here, and how much part of this force is transferred to the beam at point C. But we are not having sufficient data for that. Okay, then EI, flexural rigidity of the beam, is required. So that means that this question cannot be solved with the given data if this string is attached to the beam at this location. Okay, that means the bending moment diagram cannot be drawn. Okay, we cannot draw the bending moment diagram. So none of the options is correct. Okay, we cannot find. So in examination, if such type of question comes, however, this type of question, that means wrong question. If some wrong question comes, so wrong question comes once in 2-3 years only. Okay, not very frequently. So you can leave that question, and in gate examination we can later on challenge those questions also. Okay, but in gate examination mostly wrong questions are not there. This is in EAC, so one question was asked like this. Okay, so better to leave this type of question. Okay, so let's move forward. Next question: consider the following statements with regard to the shear force diagram for the beam ABCD. So this is the beam ABCD. Okay, so this is point C. Point C is here. Okay, this is the arrow showing the distance. Okay, so we have to consider some points. What are the points given? Let us see what are the points given. So points are given. The beam ABCD is an overhanging beam having supports at A and D only. Supports at A and D. So if there are supports at A and D, okay, and it is an overhanging beam, that means here is some support. If there is any support here, then there must be sudden change in shear force diagram at this point. Is there any sudden change? Yes, there is sudden change. Okay, so there can be a support here, and there is sudden changes here also. So there can be a support here. Okay, so we can say yes, there is support at this point and at this point. Also, these support reactions are giving me upward force, upward reaction. Okay, so here the support reaction will be 50 kilonewton. So if I calculate here, it is positive, no, positive here. Because of this, I am getting positive shear force. So positive. So at this location, if it is upward, it will give me clockwise rotation. Shear force will give me clockwise rotation, so it is positive. So yes, it is acting in upward direction. So if it is acting in upward direction, that means it is a support reaction. Mostly support reactions will give upward reaction only, mostly, okay, because loading is mostly downward only. Now at this location also we can see there that because of this reaction we are getting upward reaction, okay. So these two will be supports. That means statement 1 is correct. Statement 1 is correct. This much you have understood or not? First statement is correct. Clear? First statement is correct. Let's move on to the next statement. Just a minute. Okay. Okay, so first statement is correct. Let's see the next statement. The beam carries a point load of 20 kilonewton at C. So at point C, is beam carrying a point load of 20 kilonewton? Is there any sudden change at point C? Is there any sudden change in shear force diagram at point C? There is no sudden change here. Okay, this value at C is 20 kilonewton. That doesn't mean that there is a sudden change. Okay, the change is gradually over the span AC, and here final value is 20 minus 20 kilonewton. That does not mean that this is a sudden change. Okay, there is no sudden change. Sudden change means it is like this. Sudden change from 0 to 50 in almost zero length. Okay, from minus 20 to plus 10 in almost zero length. Here it is constant 20. Okay, so there is no sudden change at point C. That means there is no point load at C. So beam carries a point load? No, wrong. So second statement is wrong. Third, the beam carries a concentrated load of 10 kilonewton at B. So at B, I can see there is a sudden change of 10 kilonewton. At B, there is a sudden change of 10 kilonewton. That means there is a point load at point B. So this is correct. Okay, third statement is correct. Fourth statement, the beam is an overhanging beam having supports at C and D. So if we are saying that there is support at C, there should be sudden change in shear force diagram. So here we are not having any sudden change. Okay, that means at support at point C there is no support, but at D there is support. So D wala part is correct, D part is correct, but C part is wrong. So overall this statement will be wrong. Okay. Fifth, the beam carries a uniformly distributed load of 70 kilonewton over the left hand portion AC only. So this portion AC, on this portion, do we have uniformly distributed load of total magnitude 70 kilonewton? So in portion AC, I can see that shear force diagram is changing linearly. There is linear change in the shear force diagram in portion AC. So when loading is UDL, uniformly distributed load, in that portion, shear force diagram will change uniformly. In that portion, shear force diagram will change uniformly. Okay, very good. So this part seems correct, that it is uniformly distributed load. Okay, now we have to find out whether the magnitude is 70 kilonewton or not. Okay, so this much part is clear. Now we have to see if the magnitude is 70 kilonewton or not. Now what is the change in value of shear force? Here the shear force was plus 50. Here the shear force is minus 20. What is the change in shear force value? So change in shear force is 50 minus minus 20. 50 change in shear force. How much? Here we are having positive 50. So 50 minus, here we are having minus 20. So minus 20. So we are having a change of 70 kilonewton. So that means this UDL is causing a total change in shear force of 70 kilonewton. That means the total magnitude of UDL is how much? 70 kilonewton. Clear? 70 kilonewton is the total magnitude of shear force. Okay, so this is correct. This is also correct. So fifth point is correct. So our correct options are 1, 3 and 5. 1, 3 and 5. Option B is the correct answer. Option B is the correct answer. Clear to everyone? Any doubt? No doubt? Let's move on to the next. Two parallel rails are running on railway sleepers. Okay, two parallel rails. Rails means these. लोहे की पटरी. Okay, iron rails. Okay, are running on railway sleepers. Here there are railway sleepers. So these are resting on railway sleepers. Railway sleepers. These are the railway sleepers like this. So these railway sleepers are placed at some distance. Center to center gap is maintained. Okay. So these are the rails on which train will move. Okay. And these are the sleepers on which these rails are resting. So two parallel rails are running on railway sleepers. The center to center distance between the rails is B. So center to center distance between rails, this rail is B. Okay. With the sleepers projected by an amount of A at each end beyond the rails. So after the rails are over here, the projection of these sleepers is A and A on both sides. Okay. The center to center distance between the rails is B, that we have shown here, B. Okay. With the sleepers projecting, the projection of sleepers is amount A at each end. So amount A is the projection. Okay. When the train passes over the rails, so when the train is passing over the rails, the reaction exerted by the ground, so reaction will coming from the bottom. Okay. So if these are the rails like this, these are the rails. Okay, if these are the rails like this, okay, train will be running on these two rails. Train will be running on these two rails, and let us suppose these are my fingers. These fingers, equally spaced fingers, these will act as sleepers like this. Okay, these are the sleepers. Okay, so some part of the sleeper is projecting, some part of the sleeper is projecting beyond the rails, right? Okay, now. Okay, now sleeper are supported on the ground. Sleepers are supported. These are supported on the ground. This ground will be exerting a downward pressure. Okay, so the pressure from the ground will be in the form of uniformly distributed load. There will be uniform pressure from the ground on the rails. Okay, so these are the rails like this. Not rails, sorry, sleepers. These are the sleepers. So we are taking a sleeper, and sleeper will be having a uniformly distributed load from bottom. From bottom, it will be having a uniformly distributed load. Okay, and on these rails, there will be a point load from the, on these sleepers, there will be point load because of the rails. Okay, because of this rails. This distance is B. This distance is B. Center to center distance between rails is B. And this projection is A. This projection is A. Now, yes. So, further, what is asked? When the train passes over the rails, the reaction exerted by the ground can be taken as uniformly distributed over the sleeper. Okay, so this reaction can be taken as uniformly distributed on the sleeper. The ratio B by A for the condition that the maximum bending moment is as small as possible. So ratio of B by A is asked. So if I draw the bending moment diagram, how will be the bending moment diagram? If I draw bending moment diagram in this condition, so bending moment diagram will be something like this. Just a minute. Bending moment diagram. Okay, I have to draw bending moment diagram. Just a minute. Okay. So let me draw the reference lines first. Okay, so these are the reference lines. Now, okay, so bending moment diagram will be something like this. So here it is going upward. So this will be giving sagging bending moment, but it is UDL. So UDL, because of UDL, we will be having positive bending moment. Okay, and here the bending moment diagram will be like this. This will be the bending moment diagram. Just opposite of this case, when there is a beam and UDL is acting from top. Okay, so in this condition, our bending moment diagram will be like this. So this is just reverse of this because loading is just reverse. When loading here is just reverse of this one, then here bending moment diagram will be just reverse of this one, right? Now, here, this value of bending moment and this value of bending moment. So we are having the condition ratio of B by A for the condition that the maximum bending moment is as small as possible. This condition will be arising when magnitude of this bending moment, this value of bending moment will be equal to this bending moment. Okay. Now what will be the value of this bending moment? This, let us say this bending moment is M1 and this bending moment is M2. So magnitude of these two bending moments is equal. That means magnitude of M1 will be equal to magnitude of M2. Magnitude of M1 is equal to magnitude of M2. Okay. So this condition, the condition that the maximum bending moment is as small as possible, will be coming when this magnitude M1 and this magnitude M2, these are both are equal. Now let us calculate M1. In order to calculate M1, I'll be having minus W x square by 2. Okay, this here bending moment at this location will be equal to, will be because of this UDL only, because of this UDL only. Because of this UDL, it will be W A square by 2. Okay, so here M1 will be equal to W A square by 2. W A square by 2. Now this bending moment, for this bending moment, we have to calculate what is the reaction here. Okay, let us say if this is W, so this load will be W A plus B by 2, W into A plus B by 2, and here also W into A plus B by 2, A plus B by 2. So this load will be W A plus B by 2, this load will be W A plus B by 2. Now what will be the value of M2, bending moment at this location? So it will be, because of this UDL, it will be positive, and because of this load, it will be negative. Okay, so because of UDL, what is the length here? Length here is A plus B by 2. This length is A plus B by 2. Okay, so because of UDL, I will be having W x square by 2, W A plus B by 2 whole square by 2, W A plus B by 2. Okay. Now because of this point load, I'll be having negative bending moment value, and this minus bending moment value will be point load into perpendicular distance. So point load value is W A plus B by 2 and perpendicular distance is B by 2. So it will be minus W A plus B by 2 whole into B by 2. Okay. So W will be cancelled. W will be cancelled. Divided by 2, divided by 2, divided by 2 will be cancelled. Okay, so what I'll be getting finally? Finally, I'll be getting A square will be equal to A square plus B square by 4 plus AB minus AB minus B square by 2. Okay, plus AB and minus AB will be cancelled. Plus AB minus AB cancelled. A square will be cancelled. A square and A square will be cancelled. If A square and A square will be cancelled, everything will, okay, actually what will happen? This bending moment here, this will be negative. Okay, this will be negative. Okay, so negative bending moment, negative, this negative. Okay, so final will be negative. We have to take the sign convention as that. Just a minute. This value will be minus, this value will be plus. W A plus B by 2. Because of this UDL, here it is positive, here it is negative. Okay, so final answer is negative. We have to change the sign because we are taking magnitude. Okay, so because of UDL, actually I am getting positive, but I have to take negative because overall the answer is negative. Okay, so I have to change the sign of this. Okay, so minus W a plus b by 2 whole square by 2. This is because of UDL and this is because of point load. Okay, now this W will get cancelled. This 2 will get cancelled. Okay, this a square will be equal to minus of a square plus b square by 4 plus ab, and this will be ab plus b square by 2. Okay, so I am getting a square will be equal to minus of a square minus of b square by 4 minus ab plus b square by 2. Okay, so now this AB and AB will get cancelled out. Okay, this a square will come here, it will become 2a square, and this will be equal to b square by 2 minus b square by 4, it will be b square by 4. Okay, so that means we have to find out the ratio of b by a. So b square by a square, how much is b square by a square? B square by a square will be equal to 8. B square by a square is equal to 8. That means b by a will be equal to 2 root 2. B by a will be equal to 2 root 2. 2 root 2 means 1.414 into 2. So it will be 2.818. 2.818. So b by a will be equal to 2.81 or 2.82. Basically it should be 2.82, but here in option it is given as 2.83. So correct answer will be 2.83. Closest answer is 2.83. Okay, clear? Let's move on to next question. Next question. A horizontal bar of 40 mm diameter solid section is 2.4 meter long. So this distance is 2.4 meter and is rigidly held at both ends so that no angular rotation occurs axially or circumferentially at the ends as shown in the figure. Maximum tensile stress in the bar is nearly. So we have to find out the maximum tensile stress in the bar. Okay, now since these two ends are fixed, this is the case of indeterminate structure. Indeterminate structure. Okay, so this will be studied in structure analysis. In structure analysis, we will study about fixed end moments. Okay, and because of those fixed end moments and the moment at here, we'll find out what is the maximum bending moment coming in this beam. Okay, and from that we will find out the bending stress, maximum tensile bending stress. Okay, so this will be done in structure analysis. Okay, by mistake it is come in strength of materials, but it should be studied in structure analysis. Okay, so let's move on to the next question. The shear force diagram of a single overhanging beam is shown in the figure. Single overhanging beam means that at one location this can be fixed support, at this location it can be fixed support or roller support or hinge support, whatever the case may be. Okay, and there is overhang at other end. Okay, at one of the end there will be overhang, but at one end there will be no overhang, at other end there will be overhang. Okay, this is a single overhanging beam. Okay, one simple support is at A. Okay, so it is given that this is simple support and it is at A. Okay, the total downward load acting on the beam is total downward load. So wherever there is downward load, the shear force, when we move from left to right, the shear force value will drop. Whenever there is downward load, shear force will drop. Okay, in shear force diagram there will be drop in shear force. Okay, and so this is 350 Newton. This is how much? 350 plus 50, 400 Newton. So this is here at this location there is downward load of 400 Newton. there is downward load of 400 Newton here. Okay. Here we are having a downward load of 300 Newton. From 50 to 350, again it is dropping, and this drop is by 300 Newton. So again 300 Newton is the drop. Then there is, at this location, there is drop of 100 Newton. There is drop of 100 Newton. Okay. So downward load will be at this location. Okay, at this location. Here it is going up, that means it will be support, not downward load. Okay, and at this location. So 400 plus 300 plus 100. Okay, 800 Newton. So total downward load will be equal to 800 Newton. Correct answer will be option A. Option A is the correct answer. Okay, let's move on to next question. Two persons weighing W each are sitting on a plank. So this is a plank. Two persons, they are weighing W each. W. They are sitting on this plank. On a plank of length L. Okay, so length of this plank is L. Floating on water. Floating on water. So this plank is floating on water, let us say. So what will be the pressure of water? Water is acting at a point? No, water is acting uniformly. Okay, so because of water there will be a uniformly distributed load like this. Okay, at L by 4 from either side. So these two persons of weight W each are sitting on a plank of length L floating on water at L by 4 from each end. So this distance is L by 4, this distance is L by 4. Okay, from either end. Neglecting the weight of the plank, the bending moment at the middle of the plank is, so we have to find out bending moment at midpoint. Okay, so this is L by 4, total L by 2, again L by 4, again L by 2. So total length is L. So that means this distance is also L by 4. This distance is also L by 4 and L by. Okay. Now can you tell me what will be the UDL? The total downward load should be equal to total upward load. Summation Fy should be 0. Okay. So if I take that load intensity is W, small w, kilonewton per meter, small w, kilonewton per meter. Water is supporting with this intensity. Okay. So 2W will be equal to total downward load. Okay. So total downward load will be equal to, from total upward load because of water will be equal to W into L, small w into L. Okay, so small w will be equal to 2W by L. So the water is supporting with an intensity, the upward load because of water, because of buoyancy, intensity will be this 2W by L. Okay, so this is the intensity by which water is supporting, and we have to calculate value of magnitude of bending moment at this location. So magnitude of bending moment at C, let us say this point is C. Okay, so bending moment at C will be equal to, see, because of this W, I'll be getting minus. Okay, because it is giving me hogging bending moment. So minus W into perpendicular distance is how much? This distance is L by 4. Perpendicular distance is L by 4, right? Okay, now because of this I am calculating here na. So I am taking all the loads at this side. Okay, all the loads at this side. So first I have taken W. Because of W I am getting minus WL by 4. Now because of this small w I am getting how much? Now this will be giving me sagging bending moment. It will be giving me plus W into L by 2 square by 2. Okay, so let's put the value of W. Let's put the value of W, minus W, L by 4 plus small w is 2, capital W by 2L, 2 here and L from there. Okay, into L by 2 whole square. So 2 and 2 will get cancelled out. 1 L and 1 L will get cancelled out. So I'll be getting minus W L by 4 plus W L square by 2 square, L square by 2 square. So W L square by 2 square L. That means it will be L and L will cancelled. WL by 4, 2 square will become 4. So minus WL by square plus WL, minus WL by 4, minus WL by 4 plus WL by 4, I'll be getting 0. 0. Okay, so correct answer will be option D. Clear? Okay, next question. if degree of fixity at supports is lessened, the maximum hogging bending moment at ends will decrease. Degree of fixity at supports. What do we mean by degree of fixity at supports? Basically, this is also question of structure analysis, but let me give you little bit hint. Okay, we can solve it. Degree of fixity. What do we mean by degree of fixity? Degree of fixity will mean that if it is perfectly fixed support, that means there will be zero rotation here. It will not allow any rotation of the beam at this. Okay. Okay. So bending moment diagram. Can you draw bending moment diagram? Bending moment diagram is something like this. Bending moment diagram is like this. Okay. Now, this is just for comparison. Okay. This is just for comparison. So if you compare it with simply supported beam, if you correctly compare it with simply supported beam, you will be able to understand the concept. Okay. Here we are having fixed support and it is perfectly fixed support. Okay. Here we are having hinge support. That means what is the degree of fixity? Here against rotation there is no fixity. Okay. This is fixed, 100% fixed. This is 0% fixed. Okay. So that means here whatever rotation is coming, all the rotation is allowed. Okay. So this is extreme case that zero rotation is allowed, and this is how much rotation is coming, all the rotation is allowed. Okay. So this is extreme case of fixity, this is extreme case of non-fixity. Okay. Okay. So perfect rotation is allowed, all the rotation is allowed. Here zero rotation is allowed. Okay. So because here zero rotation is allowed, here bending moment is generated. Which type of bending moment? Here we are getting hogging bending moment. Hogging bending moment is generated, and at this location here in this simply supported beam, I am getting this type of bending moment. Okay. So the value of bending moment here, let us say this value of bending moment is m1, this value of bending moment is m2 here. Okay. What is this value of bending moment here? It will be, if you check, you will see that this is m1 plus m2. Okay. So whatever bending moment we are getting here plus whatever bending moment we are getting here, okay, if we add both of them, here we are getting m1 plus m2. Total bending moment at midpoint will be this. Okay. So that means in fixed beam or in simply supported beam, the total bending moment coming at the center will be, it will be like this, that some part of the bending moment here is resisted by this and some part is resisted here. Okay. Okay. So basically the total magnitude will be same. If we consider this as 0, then this value and this value will become same. Okay. So when it is 100% fixed, here we are getting a high value of bending moment, and here we are getting less value of bending moment. Okay. This is sagging bending moment, this is hogging bending moment. And if it is perfectly free to rotate, that means here we are getting zero bending moment at support, and here we are having entire bending moment is sagging bending moment at midpoint. Okay. So if degree of fixity at supports, if we lessen it, that means we are moving from this condition towards this condition, but not perfectly towards this condition, but somewhat we will be coming in between of these two. So degree of fixity at support is lessened somewhat. So our answer will be somewhere in between. If we keep on lessening the degree of fixity, that means we will be becoming more and more like this. Okay. If we are increasing the fixity, our answer will be coming more and more close to this case. Okay. So if degree of fixity is lessened, the maximum hogging bending moment at the ends will decrease. Yes or no? Yes. Now you can see that the maximum bending moment at supports will decrease. From here, from this maximum value, it will move to 0. Okay. If it is lessened by totally removed, okay, then it will become 0. But if it is lessened, then somewhat this value will decrease. Okay. Yes. So statement 1 is correct. Statement 1 is correct. Okay. Next, if degree of fixity or at support is lessened, the maximum Sagging bending moment at midspan decreases. Does this decrease or increase? So maximum sagging bending moment from here to here, it is increasing. Okay, so that means this statement is incorrect. This statement is incorrect. Okay, so A is true, but R is false. Okay, statement true, statement 2 is false. Correct answer is option C. Option C is the correct answer. Clear? Let's move on to next question. The change in shearing force between 2 points on the beam is equal to the area of. Change in shearing force. Okay. So as we have seen, change in bending moment will be equal to area of shear force. So change in shear force will be equal to area of loading intensity, area of loading diagram. Okay, so loading diagram, correct answer will be equal to area of loading diagram between the 2 points. Loading diagram between the 2 points. Correct answer will be option A. Clear? Next question. Shear force diagram of a beam is shown in the figure. So this is the shear force diagram of the beam. What we have to do? Total vertically downward loads on the beam is, so vertically downward load here, how much? 800 Newton. Okay, this is going up. Okay, so this will be going down. How much? By how much magnitude? Here the magnitude is 800 Newton. 800 Newton. Here the magnitude is 800 plus 1200. It is 2000 Newton. 2000 Newton. Here it will be 1000 Newton. Okay, so 800 plus 1200 plus 1000, how much? 3000 Newton. 3000 Newton. Correct answer will be option B. So option B is the correct answer. Clear? Let's move on to the next question. Consider the following statements regarding shearing force and bending moment. Okay, so these are some of the statements regarding shear force and bending moment. Point of contraflexure is the point where bending moment changes sign. Yes, it is correct. Point of contraflexure is the point where bending moment changes sign. Shear force is the rate of change of bending moment. Yes, correct. Shear force is the rate of change of bending moment. dm by dx is equal to v. Okay, that we know. For bending moment to be maximum or minimum, shear force should change its sign. So where shear force is changing the sign, or shear force is 0, where at whatever location shear force is changing sign, at that location dm by dx will become 0. Okay, shear force will become 0, so dm by dx will become 0. When dm by dx becomes 0, that means bending moment will be either maximum or it is minimum. Okay, maximum or minimum. So correct, this is also correct. Okay, rate of change of loading is equal to shear force. Rate of change of loading, no, dv by dx is equal to loading. So rate of change of shear force is equal to loading. Okay, this is given opposite. Okay, rate of change of shear force is equal to loading. Okay, and rate of change of bending moment is equal to shear force. Okay, so 1, 2 and 3 are correct. 1, 2 and 3 are correct. So correct answer will be option D. Okay, are correct. Also check if they are asking for correct answers or incorrect answers. Okay, next question. ESC 2021. A steel cantilever beam is proposed to build into a concrete wall. Okay, so if this is a concrete wall, a steel beam is proposed to be built into it. That means this is the steel beam and this is built into this concrete wall. That means this support will become fixed support. Okay, so this support will become fixed. Okay, so built into a concrete wall at one end and other end is free. Okay, so this becomes a cantilever beam, cantilever steel beam. It supports a dead load of 20 kilonewton per meter. So let us apply a dead load 20 kilonewton per meter and a live load of, there is live load also, live load of 10 kilonewton per meter. So live load 10 kilonewton per meter. Okay, the length of the beam is 5 meter This length is 5 meter. What are the shear force and bending moment respectively? Take yield strength. Do we need yield strength here? No need of yield strength. Okay. So what are the shear force? So basically shear force will be changing along the length. Bending moment will also be changing along the length. But they have not given at what point we have to calculate shear force, at what point we have to calculate bending moment. So at what point we will calculate? So obviously it will be this point at fixed support only. Okay. So we have to calculate maximum shear force, maximum bending moment. Okay. So what will be the value of? Now let us take total load. Loading intensity will be W is equal to 30 kilonewton per meter. 30 kilonewton per meter. So at this location, let us draw first of all shear force diagram and bending moment diagram. So shear force diagram will be like this, linear. Okay. Bending moment diagram will be parabolic. Shear force diagram will be positive. Shear force diagram will be positive like this. A minute. Okay. So shear force diagram will be positive. Here I will be getting positive value. Okay. So what is the positive value here? The positive value here is 30 into 5. 30 into 5. So 3 5s are 15. 150. 150 kilonewton meter. 150 kilonewton. Okay. Shear force and bending moment respectively. 5 meter. It should be 150, but they might be asking at some other location. Just a minute. Okay, just a minute. So might be they are asking at 0.75 meter. It is not given, it is not clear at what location they are asking, na? Okay. So from 22.5 kilonewton, 22.5 kilonewton, we can guess there might be some mistake in the question and there might be some typing error. Typist might have made some mistake. Okay. So here, let us say this distance is 0.75 meter. So at 0.75 meter, the value of shear force will be how much? 30 into 0.75, that will become 22.5 kilonewton. Now if we calculate bending moment at same location, bending moment, it will be equal to W x square by 2. So what will be the value of W? W will be equal to 30 into 0.75 square by 2. So 15 into 0.75 square, 15 into 0.75 square, so 8.43. There is some mistake in this question. Okay. If we calculate bending moment here, it will be 30 into 5 square by 2, 375. Okay. There is some mistake. Okay. So leave this question for now. I will check all the data for this question later on, and I'll again solve this question in some later class. Let's move forward for now. Now, which one of the following statements is not correct regarding the relationships between bending moment, shear force and applied load? Okay, which of the following statements is not correct? Okay, so pay attention to this, not correct. Okay, now the rate of change of shear force along a beam is equal to the distributed load. Rate of change of shear force, rate of change of shear force along the beam is equal to the distributed load. Yes, correct. This is correct. Okay, we have to find out the answer which is not correct. So this is correct. Rate of change of bending moment along a beam is equal to shear force. So dm by dx is equal to v. Okay, this is also correct. Rate of change of bending moment along a beam is equal to the distributed load. So this is not correct. Okay, shear force and bending moment at free end is always 0. Yes, this is also correct. Okay, so not correct answer, not correct is C. So our correct answer will be C only. Okay, clear? Let's move on to next question. A cantilever beam of length L is loaded by a transverse load varying linearly from W naught, at fixed end and 0 at the free end. Okay, cantilever beam, length is L. Okay, loaded by a transverse load, like this, loaded by a transverse load varying linearly from W naught at fixed end, 0 at free end. What is the shear at L by 2? So shear at L by 2. What is shear force? At L by 2, how much will be the shear force? So total force either to the right of the section or to the left of the section. So if we calculate towards the left of the section, it will become difficult. Okay, so better to calculate towards the right of the section. Now what is the loading intensity here at L by 2? This distance is L by 2. This distance is L by 2. Okay, now the loading distribution is given from 0 to W naught, over the length L. So over the length L by 2, in length L by 2, it will go from 0 to W naught by 2. It will go from 0 to W naught by 2. So at this point, it will be W naught by 2. So if loading intensity here is W naught, loading intensity here will be W naught by 2. Clear? Okay. Now, total downward force towards the right of this section, total downward loading towards the right of the section will be equal to shear force at this section, and that will be equal to area of this triangle. So area of this triangle will be half into base into height. Okay, so W naught L by 8. This will be the correct answer. W naught L by 8. Correct answer will be option D. Clear? Okay, let's move on to next question. A cantilever beam of 4 meter span carries 3 point loads of 1 kilonewton, 2 kilonewton and 2 kilonewton at 2 meter, 3 meter and 4 meter from the fixed end. Cantilever beam of 4 meter span. Okay, so let us take, this is a cantilever beam. Span is 4 meter. So it is carrying a load, point load of 1 kilonewton, 2 kilonewton and 2 kilonewton at 2 meter. So 1 kilonewton load is acting at 2 meter. This distance is 2 meter. Okay, 3 meter. So at 3 meter we are having 2 kilonewton load, and at 4 meter, that means at the free end we are again having a load of 2 kilonewton. Okay, so this is 2 meter, this is 3 meter and this is 4 meter from the fixed end respectively. What is the bending moment at 3 meter from fixed end support? So bending moment at distance of 3 meter, that means at this location, what is the bending moment? So at this location, bending moment will be equal to how much? Bending moment we can take either towards the, from the left of this section or from the right of this section. So towards the right, if I am taking, I will be getting bending moment is equal to 2 into this perpendicular distance. So 2 into perpendicular distance is 1 meter. So 2 kilonewton meter I am getting. Bending moment is equal to 2 kilonewton meter. Okay. Now, sagging or hogging and anti-clockwise, clockwise they have given. The bending moment will be considered as sagging or hogging. Okay, not clockwise and anti-clockwise. Clockwise and anti-clockwise will be moment, not bending moment. But here, since they are asking clockwise, anti-clockwise, so this will be giving me clockwise rotation. So 2 kilonewton meter clockwise. This distance is 1. Again, I think there is some mistake in this question, because if this is 2 kilonewton, then answer will be 2 kilonewton meter. Maybe this is 4 kilonewton, maybe, or it will be 3 kilonewton. There might be typing error, na? So this is 3 kilonewton. Okay, this will be 3 kilonewton. Okay, So 3 into 1, correct answer will be 3 kilonewton meter, and it is in clockwise direction. So 3 kilonewton meter clockwise. Correct answer will be option C. Now there can be one more possibility. There can be one more possibility. What possibility can it be? There can be one more possibility that beam is like this. This is 2 kilonewton. If it is 2 kilonewton, it will be 2 kilonewton. If 2 kilonewton, then here, then it will become what? Anti-clockwise. Then 2 kilonewton meter anti-clockwise will be the correct answer. So I have to verify the question. Okay. So what concept you understand now? Okay. Concept you have understood that either it will be 3 kilonewton. Okay. And if it is 2 kilonewton, then we have to draw the beam like this. We have to draw the beam like this. Okay. So let us keep the original question only. Let us keep the question as original question. Okay. This is the fixed support, and on this fixed support, this one. So beam is like this. My beam is like this. Okay. So 2 kilonewton. Here 1 kilonewton. Here 2 kilonewton. Okay. This distance is 2 meter, 3 meter, 4 meter. Okay. So at this location, this is 1 meter. At this location, I have to find out moment. So it will be anti-clockwise. So 2 kilonewton meter anti-clockwise moment. Okay. So correct answer will be option D. Okay. We have to draw the beam like this. Then it will be correct. Okay. Let's move on to next question. Simply supported beam of 9 meter span carries a point load of 30 kilonewton at 2 meter from the left end. So we are having a simply supported beam. Span is 9 meter. 9 meter. Carries a point load of 30 kilonewton at 2 meter from the left end. So here they have given from the left end, right? So 2 meter from the left end, what is the load? 30 kilonewton load. 30 kilonewton load at 2 meter from the left end of the support. It also carries a UDL of 12 kilonewton per meter over 4 meter span from the right support. Okay, from the right support over 4 meter span, we are having UDL of 12 kilonewton per meter. What is the value of shear force at 5 meter from the left support? So 5 meter from here. So at this location only. 5 plus 4 is equal to 9. So at this location, we have to find out what is the value of shear force. Okay. So either we can calculate from this side or we can calculate from this side. So I have to calculate. Let us calculate from this side. Okay. So here support reaction, let us say this is A, this is B. Okay. So if I want to calculate RA, what I have to do? Summation of moment about B equal to 0. Summation of moment about B equal to 0. This I have to do. Okay. So RA, this is RA. RA into 9. RA into 9 minus 30 into 7. Minus 30 into 7. Minus 12 into 4 square by 2 is equal to 0. So RA will be equal to 30 into 7 plus 12 into 8 whole divided by 9, 37.56. 37.56 kilonewton. Okay, so this is support reaction at RA. Now I have to calculate shear force here. So 37.56 minus 30. Something wrong with the 2023 questions. Okay, no, they are not properly checked. RA into RA into 9 minus 30 into 7 minus 12 into 4 square by 2. Okay, so 30 into 7 plus 12. Okay, 12 into 4 4s are 16, 16 by 2, 16 by 2. Okay, 3 divided by 9, 34. 34 is the answer. Calculation mistake, 34 kilonewton. Okay, so 34 kilonewton. This is RA. Now shear force, let us say this section is C. Shear force at C will be equal to RA minus 30. RA minus 30. What is the value of RA? 34 minus 30 will be equal to 4 kilonewton. Okay, so correct answer will be option A. Option A will be the correct answer. Clear? Let's move on to next question. Which one of the following statements is correct? The rate of change of shear force along the length of the beam is equal to bending moment. This is repeated, I think. 3. Okay, so same question is repeated in 2022 and 2023. So in ESE you can see, earlier it was asked not correct. Okay, here they are asking which one of the statement is correct. So rate of change of shear force along the length of the beam is equal to bending moment. This is wrong. This is wrong. Similar question, not exactly same, but similar question. Bending moment is 0 where the shear force changes sign. No, bending moment is maximum. Maximum or minimum. Okay, so this is also wrong. Shear force changes abruptly at the point of application of couple. Wrong. At the point of application of point load. Shear force changes abruptly means suddenly. There is sudden change in shear force at the point of application of point load. Okay. Rate of change of bending moment changes abruptly at the location of point load. Okay, so rate of change of bending moment, what do we mean by rate of change of bending moment? This will be equal to shear force. Rate of change of bending moment will be equal to shear force. So shear force changes abruptly. Shear force changes abruptly. This means shear force changes abruptly at the location of point load. Yes, I have already told you. So this is correct answer. This is correct answer. Rate of change of bending moment will be equal to shear force. So shear force changes abruptly at the location of point load. Okay. Cantilever beam is subjected to point load against gravity at its free end. Cantilever beam is subjected to point load against gravity. Okay, so this is the point load at the free end acting. Variation and nature of bending moment will be. So variation and nature of bending moment. Bending moment diagram will be like this. Variation is linear. Variation is linear and nature is this negative. So this will be hogging. Okay, so linear and hogging. Correct answer will be option A, linear and hogging. So very easy question, ESE 2023. So these were all the questions in today's class. So the second chapter is also complete. Shear force and bending moment diagram is complete. We'll meet in the deflection of beams next chapter, and that is very important chapter from gate perspective. It is very important chapter. Okay, so from next class, don't miss any class if you want to clearly understand all the concepts of deflection, slope and deflections of beams. So classes are held regularly on Tuesday, Thursday and Saturdays. Okay, Tuesday, Thursday and Saturday there are regular classes held. Okay, so we'll meet in the next class. Till then, bye bye, take care. Thank you, GW Soldier.